of my problem, I have a tiny plastic bead and it is given the total charge of negative 6.4 times 10 to the negative 19th power. And then my problem itself is how many excess electrons are on the bead. So for my problem, I tried to use stuff that was in the earlier parts of this project and bring it into this problem to really tie it together. So that is what I'm stating here, that Thompson and Millikan used to show the whole number multiples. And so for my benefits of my problem, I have that it helped people understand objects can get charged by adding or removing electrons. And then with solving my problem, because it's not too hard, it's not too simple, it'll teach you the basics of scientific notation and dividing them by the electron charge. And you can also use my problem to expand on, because after this someone can solve other charge problems, like finding how many electrons move in a current or how much charge an object has. And so for my development of my problem, I made my problem by choosing a small realistic charge. It's not too simple because you still have to divide using scientific notation. It uses one formula, m equals q divided by e. The hardest part was finding a number that wasn't already in the book or another student had. I tried to make it kind of unique in its own way. And that brings me to my uniqueness of my problem. My problem is unique because I picked the formula here. It gives real calculations. It's not an obvious answer you have to solve for it. I added my own numbers and my own scenario. And then this is my visual for my problem. I created a graph here. So this graph shows how the total charge becomes more negative as more electrons are added to the bead. And then the straight line here, it shows that every added electron increases the charge by the same amount, so it's a consistent graph as well. And this shows that charge comes in equal steps, not fractions. And so that brings me to my formula for my problem. Here I have everything that needs to go with my formula. So for my main formula, I have Q equals M times E. And then Q itself stands for the charge on the bead. N stands for the number of electrons, and E stands for electron charge. And then the constants are shown here. It is E 1.602 times 10 to the negative 19th power. And so to solve this problem, you would need to rearrange the formula to Q divided by E, which then equals N, the number of electrons. So for my solution of my problem, I'm given the formula here, and then you have to rearrange it, and then you know the constant. So with doing all of this, the final answer would be 4 excess electrons. And then the negative charge means that the bead gained electrons because electrons are negatively charged. And so here's my verification for my problem. And so you also, whenever you're verifying your problem, you want to make sure that your units are correct, because that can determine the whole accuracy of the problem itself. And so whenever you are getting your answer for electrons, it must be a whole number, because electrons cannot be split. It's either 1 or none.
Okay, hi y'all. So, get me out the way. Okay, this is my part D. Okay. So for part D, I created my own original numerical problem related to electron charge. My problem asks if a tiny metal sphere carries a charge of negative 4.8 times 10 to the negative 19 coulombs, how many extra electrons are on the sphere? This connects directly to what we've been studying, because electron charge is always a multiple of the fundamental charge. And this is my 4.1. This problem is relevant to the topic because it uses the actual real value of the electron charge. 1.602 times 10 to the negative 19 coulombs. Scientists like Millikan first measured this number, and my problem shows how that value is used to figure out how many electrons are on the object. I'm sick. Okay, so it ties back to the idea that charge comes in the whole package. Okay, that was 4.1. Benefits of the problem. The benefit of solving a problem like this is that it helps you understand the electric charge is quantized. Quantized. Whatever. You also get practice using scientific concepts, and this skill is helpful for harder problems involving electric fields, electric force, and circuits later on. It shows how many microscopic values connect to real objects. And here's my picture and then my citing at the bottom. Development of problem. I'm gonna move myself over here. I developed my problem by starting with a real physical constant, which is the charge of one electron. Then I chose a charge value for the sphere that is realistic but still requires some work with scientific notation. It's not too easy because you have to divide powers of 10, but it's not too hard because it only uses one formula. I also avoided using any standard textbook numbers to make sure it stayed original. Here's my picture at the bottom of my citing. This of the problem. 4.4 uniqueness of a problem. My problem is different from common textbook problems because I created a charge value. I chose a realistic but unique charge that equals 3 electrons. And my problem goes beyond examples because it connects electron counting to a physical object, not just abstract math. That's my little insight on my problem, the differences in my problem and others. Visual. I just created a chart. I use a simple table that shows how the total charge increases as you add on more electrons. It's clear that charge increases in steps or multiplies of the electron charge. My problem charge lines up perfectly on the table, which helps explain why the answer is what it is. Here's my formula for the problem. To solve the problem, I use formula Q equals N times E. Q is the total charge on the sphere, N is the number of electrons, E is the charge of one electron. Because I needed to find E and I rearranged the formula to N equals Q divided by E. It's my formula. Here's a picture of my citing. My solution. And I'm not covering anything. My solution, I plugged in the values negative 4.8 times 10 to the negative 19 coulombs divided by negative 1.602 times 10 to the negative 19 coulombs. The negatives cancel out, the powers of 10 cancel out, and the numbers divide to about 3. So the sphere has about 3 excess electrons. Verification, like right here. Okay. So to verify the answer, I multiply the number of electrons back by the electron charge. 3 electrons times 1.602 times 10 to the negative 19 coulombs gives almost exactly the original charge. The units match, the value makes sense, and it confirms that the answer is reasonable.
Hi, my name is Julissa Costa, and I'm going to be doing my part D of the project. So, the relevance of the problem. My problem is a charged oil droplet has a mass of 2.5 times 10 to the negative 15th power kilograms and falls with constant velocity when the upward electric field is 3.2 times 10 to the fourth power newtons per coulombs. Calculate the electric charge on the droplet. So that's going to be my problem, and the relevance to the electron charge is to find the solution. This problem uses the exact way that Millikan used to find the electron charge. It also needs to be solved experimental data and not just like memorizing anything or just guessing something to find the answer. And this problem also shows how the oil drop cause drops at a constant velocity when the forces cancel out. The benefits of this problem is it's going to help you understand how Millikan measured the electron charge doing this problem, because you're going to have to obviously measure your own droplet in this problem. And also it will demonstrate the connected fields between electric fields and gravitational force and charges. Some skills gained from this problem is you would get a better understanding of upward and downward forces, and also using the skills for scientific notation and force balance. Other problems that this could help in is going to be able to understand mass to charge ratios and just being able to calculate how many electrons are in a particle. Now for the development of my problem, I chose this mass smaller than what it usually is on like the textbooks, and I chose something that actually requires you to do calculations and isn't really that easy. I didn't choose something too simple because what would be the challenge in that, and then I didn't choose something that's too difficult because I didn't want it to be too difficult to solve, given that you only use one formula and it's just basics, like basic parts of math. Some difficulties I did find developing in the problem was something I had to come up with something that wasn't already in the textbook, which was a difficulty and something that hasn't really been common and already used everywhere. Now on to my uniqueness of the problem. My problem is different from the other common problems is because you have to actually have an understanding to solve the problem, and then most of the oil drop questions that they have right now are motionless, suspended, and this problem uses the constant downward velocity. My problem goes above and beyond because it makes you think about difference of forces. It uses the equations the way Millikan used and scientists used to find the electron charge. And some of the elements added was does not have a common mass value in the equation, and this is the droplet actually moving, and electric field is upward and not downward like most of the questions are, so that's why it's unique. Now this is the visual of my problem. The graph here, you could just see that it's calculated charges, which is the Q, and how it changes with different values of the electric field, which is the E for the oil droplet mass of 2.5 times 10 to the negative 15 power in kilograms. You could also see that as the electric field increases, the electron charge does decrease. And this is kind of an idea of how Millikan could have analyzed or even graphed his own like data when he was doing his experiment. Onto the formula of the problem. The formulas are just force balance, solving for charge, and then the variables: Q, the charge of droplet in coulombs, M, droplet mass is in kilograms, and then G, the gravitational acceleration in meters per second squared. E would be the electric field in newtons per coulombs, and in the units that they're measured in, the charge is measured in the coulombs, mass is in kilograms, electric field is newtons per coulombs, and then the weight force is in newtons. And the constants is G equals 9.8 meters per second squared. And now onto the solution for the problem. The first step is the droplet falls at constant velocity, meaning the net force is 0. So then the second step is solve for the charge. So Q equals mg divided by E. So you just plug them in, substitute the values obviously. So m equals 2.5 times 10 to the negative 15th power in kilograms, and then G equals 9.8 meters per second squared, and E equals 2 by 10 to the 4th power newtons in coulombs. And then step 4 is you're going to commute the weight, and then step 5, commute the charge. You're going to solve it, and then the final answer would be 7 by 7 by 10 times 10 to the negative 19 power in coulombs. This is the verification for the problem. The final calculated charge would be Q equals 7.7 times 10 to the negative 19th power in coulombs. The electron charge formula would be E equals 1.602 times 10 to the negative 19th power of coulombs. And then so you verify, you do the equation right here, and then that would just basically means that the droplet carried about 5 electrons, just how in Millikan's experiment stated, his change always came in smaller integer multiplies. And that basically just sums up my part of my problem.
Relevance of the problem. This problem connects the abstract concept of electron charge to a measurable quantity in real-world devices. It reinforces the idea that electric charge is quantized, not continuous. The problem is based on a common scenario in electronics, determining how many electrons are transferred when a known charge is stored. This directly relates to the project topic by showing how the elementary charge E equals 1.602 times 10 to the negative 19th power is used to calculate the number of electrons in a system. This problem builds on earlier slides that introduced the definition and significance of an electron charge, now applying it in a numerical context. Problem statement. A metal sphere is given a charge of 3.2 microcoulombs. How many excess electrons are on the sphere? Benefits of problem. Solving this problem helps students understand the scale of electric charge at the particle level. It builds fluency with scientific notation and unit conversions, both essential in physics. It compares students to analyze current, capacitance, and electrostatic interactions in later coursework. Understanding this problem helps in fields like electronics, nanotechnology, and material science. Once mastered, students can extend this calculate current, drift velocity, or even charge density in conductors. Development of problem. The problem was developed by starting with a realistic charge value used in small electronic components. The elementary charge was used as a conversion factor to determine the number of electrons. The problem avoids being too simple by requiring scientific notation and unit awareness. It avoids being too difficult by focusing on a single-step calculation with a clear physical interpretation. Care was taken to avoid multiple choice or fill-in-the-blank formats, ensuring the student must perform and explain a real calculation. Uniqueness of the problem. Unlike textbook problems that often ask for the charge on one electron or proton, the problem scales up to a macroscopic object. It includes a real-world context, making the concept more tangible. It introduces the idea that even small charges involve billions of electrons, which is rarely emphasized in standard problems. The problem is not copied from any other source and was designed to be original, relevant, and instructive. It adds value by connecting atomic scale constants to everyday physical systems. This was the chart that I did. The graph shows a linear relationship between charge and number of electrons. This visual reinforces the idea that charge is quantized and accumulates in discrete steps. Each point on the graph corresponds to a real-world scenario involving stored charge. The slope of the line is 1 over E, showing the inverse relationship between charge and elementary charge. So the main formula is N equals Q divided by E, where N equals the number of electrons, Q equals the total charge, and E is the elementary charge. The consistents are E. Units Q must be converted from microcoulombs to coulombs. This formula is essential for converting between macroscopic charge and microscopic particle count. Solution for problem. So given Q equals 3.2, then it shows that the 3.2 times 10 to the negative 6 power, and then E equals 1.602 times 10 to the negative 19th power. The step 1 is N, Q divided by E, so N equals 3.2 times 10 to the negative 6 power divided by 1.602 times 10 to the negative 19th power. then you just calculate that out, and it would be N equals 1.9975 times 10 to the 13th power electrons. Final answer is approximately 2.0 times 10 to the 13th electrons are on the sphere. This shows that even a small visible change involves trillions of electrons. Verification for problem. The units cancel correctly, C over C, unitless number of electrons. This results in the unexpected range for microcoulombs level charges. The answer is reasonable. Trillions of electrons are typical for microcoulomb charges. This solution demonstrates how the concept of electron charge is essential for understanding electrostatics and current behavior. It ties back to the project's core theme, how a fundamental constant governs a real-world electrical system.